In this problem, we have two forces, FB and FC. They both direct from point A, but to point B and point C respectively. And their magnitudes are given. The positions of points A, B, and C are also given. And in this problem, we need to determine the resultant force of FB and FC. And we also need to determine the angle between them. So in order to do that, we'll first represent both forces as Cartesian vectors. So let's take FB as an example. In order to determine FB as a Cartesian vector, we recognize that this equals to its magnitude, which is given, multiplied by a unit vector. And this unit vector points from A to B. And this unit vector is also along the same direction of a position vector that is pointing from A to B. In other words, if we can find the position vector RAB, then we can find the unit vector UAB, and then we can find the force vector. So that's the strategy. So this is the same strategy that applies when you're trying to find the force vector. When you know the force vector is directed along a cable, like in this case, and you know two different points along this cable, and the two different points will give you the direction of the cable, which will lead you to the unit vector and then eventually the force vector. So to determine the position vector RAB first, we need to find the coordinates of A. We read the coordinates from here, so that'll be positive 2, 0 along the y direction, positive 6 along the z direction, so 2, 0, 6. And then we read the position, the coordinates for point B, that'll be 0 along the x direction, 4 along the y direction, and then 2 along the z direction. So in order to find the position vector RAB equals to, we take the coordinates of the end point minus the coordinates of the start point. So we find the difference in the coordinates at the point B. In the x direction, that will be 0 minus 2, and that is along the x direction, therefore it has the unit vector of I, plus next the y coordinate of point B, the end point, 4, minus the y coordinate of the beginning, the start point, 0, that is along the y direction, therefore it has a unit vector j. And lastly, the z coordinate of the end point, which is 2, minus the z component coordinate of the start point, which is 6. And that is along the z direction, therefore it has a unit vector k. So this equals to negative 2i plus 4j minus 4k. This does have a unit because it's a position vector. In this case, the position vector has a unit of foot. And then because we have RAB, we can calculate its unit vector that points to the direction from A to B with a magnitude of 1, which equals to RAB vector divided by its magnitude. And that equals to RAB, it's on the numerator. On the denominator, that will be the square root of negative 2 squared plus 4 squared plus negative 4 squared. And as you can see, I didn't write the units on the numerator and the denominator. That is because both numerator and denominator are lengths. Therefore, they have the same unit of foot. Therefore, they cancel out anyway. A unit vector is always dimensionless. So the denominator in this case is simply 3. Therefore, 6. Therefore, this unit vector is negative 2 over 6, so negative 1/3 I, and then plus 2/3 j minus 2/3 k, dimensionless. So from here, FB equals to its magnitude times UAB, which is 600 pounds multiplied to the three components of UAB. Therefore, that equals to negative 200I plus 400J minus 400K. It has a unit of pound. So now we have successfully expressed FB as a Cartesian vector. We're going to follow a similar approach for FC. So following the similar approach, which means that we find RAC, we find RAC, and then we find UAC, and then from there we find FC as a vector. So following this similar approach, FC equals to negative 420 I plus 210J minus 140K. So from there, we can find the resultant force. The resultant force simply equals to FB plus FC. We just add their x, y, and z components together respectively. So the first term is negative 620I. The next term is 610J. And lastly, 540K in the unit of pound. So that answers the first question. For the second question, the angle between the two forces. So to determine the angle between any two vectors, even if the vectors do not intercept with each other, we use dot product. Therefore, the angle between cosine theta equals to the dot product of B and C divided by the magnitude of FB and the magnitude of FC. To determine the dot product, basically you multiply the corresponding XYZ terms together and then add them together. So basically it's the sum of the products of the corresponding X, Y, and Z components of the two vectors. So in this case, we have negative 200 multiplied by negative 420, that's the first term, plus 400 multiplied by 210, that's the second term, plus negative 400 multiplied by negative 140, that's the third term, divided by FB and FC are both given, that's simply 600 multiplied by 490. So this right here equals to 0.7619. So from here, theta equals to inverse cosine or arc cosine 0.7619, and that is 40.4 degrees. If you know the two unit vectors UAB and UAC, then theta, cosine theta also equals to simply the dot product of UAB and UAC divided by their magnitudes, but their magnitudes are both 1 anyway. So this should give you the same result.